So we're going to talk about what we have in the world, and then we're going to go to the basic structural analysis that pretty much you will see most of the world uses ASHTO 93. So ASHTO 93 design is by far the most common in the world. I've been to the world, so there is outside the United States, it's the most. So let's try to understand that very quickly. I know some of you are already aware of this and you're knowledgeable, but just let's talk about it. I'll highlight certain components of that ASHTO 93 design that will allow us to make an analogy between ASHTO 93 to payment ME design. Now, then, this is an important session that I'll cover. Payment structural analysis. So payment structural analysis, just like in the structural analysis of the buildings, it's extremely important, and that is a key part of most of the mechanistic empirical payment design guide approaches. Because payment ME software is one of them, but there are many other actually mechanistic empirical payment design approaches. Because of complexity, some of them are implemented, some of them are not implemented, but there are many out there. But the core is this payment structural analysis. And if you are a payment designer, I strongly encourage you to be very proficient in what structural analysis means and how it works, and what are the, not necessarily the equations on coming up with stresses and strains, but actually you should have a software that you can use outside whatever the design software that you're using. That's why I sent these links. One of the links is the WinJulia, which is a free software that is inside the payment ME software, and also one of my softwares for structural analysis. So you can use them in the future in your designs or in your checking of the design calculations. Now then, we're going to actually get into the payment ME software. Payment ME software is by far the best payment design software out there in terms of not necessarily just accuracy. You know, there are more accurate softwares out there, obviously, but best, quote unquote, best meaning in terms of simplicity. So it's simpler than some others that did not pick up in other, very complicated softwares out there. But it is also complicated, very complicated compared to ASHTO 93 and some other design softwares. And it looks like this is the gold standard in the world right now. So we're going to talk about the payment ME inputs. Payment ME inputs, unfortunately, are extremely complicated. There are lots of inputs that you need to understand before use. So that's partially why we are here. So let's try to understand what these inputs are, how sensitive the outputs to these inputs are also. And local calibration is a mandatory step in using payment ME. So this is important also. We'll talk about that. And I'll end with a whole bunch of example designs, example analyses that we have done with the payment ME, and I'll try to show how useful payment ME type softwares are. Now, payment structural designs, typically in a nutshell, at the end of the structural design, what we are looking at is, let's come up with a number of layers, how many layers we want, thicknesses of each layers, and types of the materials to be used in each layer. So in a nutshell, that's what we are coming up at the end. Now, I want to contrast that with material design. Material design is the asphalt mixture design, the super pave mix design we did yesterday, like determination of asphalt binder content and aggregate gradation. This is what we did yesterday. So we came up with what should be the aggregate blend and what should be the design binder content to get to this mixture level. And also for aggregate soil mixture design, meaning for the base and sub-base, we have aggregate gradation, limiting the plasticity and swelling on the subsurface, aggregate base and subsoil as well. So these are done completely separately than this one. So these two, structural design and material design, are currently in all around the world are separate. They are not combined. So material design you know, a bunch of people who does the design, super pave design, mixed design, and there is the pavement designers that are separate. Ideally, that shouldn't be the case. They should be working together, and you should be coming out with the mixed design relative to the pavement design. But they are getting together with the introduction of pavement and software. These two parts of the pavement design, material design and pavement structural design, they are coming together closer and closer, and eventually, hopefully, they will be all together. So when they are all together, there is something called performance-based specifications or performance-based designs. In performance-based designs are essentially, it hasn't picked up everywhere yet, but it has been picked up in some places. Performance-based design essentially says, okay, we don't care what mixtures you mix, so we don't care what your aggregate blend and binder content is. We are not going to specify this for you. You have the responsibility to come up with a mix that will have a certain property, such as the dynamic modulus and certain flow number characteristics. We don't care what the ingredients are, but when I place that in structure, it should give you the performance that you want. So you essentially come up with the, let's say in a sense, let's say for asphalt layer, dynamic modulus or modulus of the asphalt layer, and then you design your structure or material that will give you that modulus that you are designing for. So that is, you know, that is being experimented at certain places, but not very wide right now. So right now they are all kind of separate from each other. Now, pavement design procedures all around the world. There are three main approaches. The first approach is the empirical approach. Just empirical approach. Okay, what is the empirical approach? You know, it's as simple as like local municipalities. They say, okay, I know this road really well. When I put 4-inch road, it always works. So I know I'll always put 4-inch road here. Okay, that's it. That's pretty much it. I know, based on knowledge of that environment, and it seems to be working and all that. So now empirical approach is also, AASHTO 93 is also another empirical approach. So what is the definition of empirical approach? Essentially, result of the systematic collection of condition data over a period of time and the statistical correlation of design variable with this performance information. So a perfect example is the AASHTO road test, where AASHTO 93 design is based on. So there was an AASHTO road test, there was a big road test, and this road test, a whole bunch of pavements with different structures were tested in Illinois, and their performance have been monitored over time, their structural performance, their thicknesses, and the distresses are correlated, and that's where the AASHTO 93 design comes from. Analytical approaches are, they employ a pavement response model, like the layered elastic model we're going to talk about today, to calculate stresses and strains induced by a wheel load, typically a 18 kip single axle load, typically, but not everywhere. Sometimes people use multi-axle also. These calculated values are compared with permissible values. So the way that it works is, okay, let's say we want to design a road with a certain thickness. Let's put an 18 kip load. What kind of strain do we expect at the bottom of the asphalt layer? And okay, we don't want that strain to be more than X amount, whatever that X amount is. 100 microstrain, 150 microstrain. So that's how it is based on. So it's based on the structural analysis of the structure. Of course, this is very nice. And the permissive values are obtained from a back calculation of structures that are known to perform well. So, you know, in the field, what they do is they come up with these strain values. So they go and look at the field performance of some of these sections in their region. Let's say if you're in Germany or, you know, or Qatar or wherever, you look at the good performing roads and bad performing roads and look at what the strain levels you experience with relative to the thicknesses, and then come up with some kind of a threshold. Okay, so these are the strain levels at the base of the asphalt we don't want to exceed, kind of a thing. Now, mechanistic empirical approaches are used to, they include mechanistic and empirical. So it kind of combines both of them, analytical and empirical approaches. So there are performance models, just like, one of the performance models is this analytical model. And there are others out there also. And pavement deterioration with time is essentially predicted. Now, in this case, this mechanistic empirical approaches, they require input data obtained from laboratory tests. So you have to come up with some kind of a database of laboratory tests on asphalt mixtures, soils, whatever the materials you're going to use. You need to have a database of materials, and you need to use that information to design the roads. And the better ones, like the Pavement ME software, they predict actual performance, such as fatigue cracking percentage, longitudinal cracking, feet per mile, and terminal cracking, and so on. So, under specified traffic and climatic conditions. So, the advanced ones, like Pavement ME software, they actually use the historical traffic data and historical climatic data to project the traffic and climate for the future, next 20 years or so, to and run lots of simulations, prediction simulations, to find cracking with time or rotting with